Okay, today is March 2nd, and we are beginning our gas laws. Our objective is the students will understand and describe the postulates of the kinetic molecular theory as they relate to ideal gases and real gases. So today we talked about the kinetic molecular theory. This theory attempts to explain gas properties and behavior in a perfect situation. We call that ideal gases. Okay, ideal gases occur in the perfect situation that we'll talk about in a little bit. The 5 statements of the theory, what I want you to know is I want you to know all 5 postulates as they relate to the ideal gas, to both the ideal and real gases. Okay, that's what our take home from this is. All right, so we know ideal gases are perfect situation and the 5 statements. So I want us to know all 5 as they relate to both ideal and real gases. So the first one that we study is the molecules of an ideal gas are dimensionless points. In other words, they have no volume. Today in class, I produced carbon dioxide gas, was able to scoop it up and empty it over flames and put the flames out. So this does not occur with real gases, only ideal. Then the molecules of an ideal gas move in a constant, random, chaotic straight line. A constant, random, chaotic straight line. So if you do a gas with your hands, you can remember when we did that, you can see it's chaotic, it's random, it's constant, and they go in a straight line. And this will be real and ideal gases. The third postulate is the average kinetic energy. That kinetic energy is the energy of motion. So the average motion of an ideal gas is proportional to the average temperature in Kelvin. And later on in the page we'll talk about the Kelvin scale. The Kelvin scale being the only scale that measures the motion of particles. So a proportion is a direct relationship. If you're in Algebra 2, you've learned direct and inverse relationships. In a direct relationship, the change occurs in the same direction. The change occurs in the same direction. Okay. Meaning when one goes up, the other goes up. Okay, and this is for real and ideal gases. All right, so the fourth postulate is when ideal gases collide with each other, the collisions are said to be elastic. We have elastic collisions. This will be a test question. What type of collisions do gases have? The collisions, they are elastic collision, which means the total energy stays the same. So as they bump into each other, one may transfer that energy to the other one, but the total energy stays the same. We have no energy lost. And this is true for real and ideal gases. Real and ideal. Lastly, the molecules of an ideal gas do not attract or repel each other, meaning that they have no forces. Well, we know that that's incorrect for real gases because real gases, as we remove energy from the system and they slow down, the particles begin to attract, and that's how they become a liquid. So this is not true for real gases, only true for ideal gases. So in reality, the 2 statements that do not apply to real gases are number 1 and number 5. And that is because real gases have volume and forces. All right. So this next group, this will be an essay type question on your quiz, on your test, etc. A real gas, the question will be, when does a real gas behave like an ideal gas? And your answer will be, a real gas will behave most like an ideal gas, meaning it has no volume and no forces if the temperature is high and or the pressure is low. And you'll have to explain that. And the explanation is because at high temperatures, the molecules or particles are moving so fast, they stay far apart from each other, so you can't measure volume. And then at the low pressure, the particles can spread out so forces are not detected from each other. So the explanation is, at high temperature, the particles move faster and stay farther apart. Therefore, volume cannot be measured. Then, at low pressure, the particles can spread out, so forces are not detected by the particles. All right, so that's the kinetic molecular theory. I need you to be able to describe and understand these 5 postulates as they relate to real and ideal gases. Now, the second part of the gas law notes are the variables. Okay, we're going to talk about the 5 variables, and we're going to put this in our foldable that we made today too. So the variables are, the first one is the number of particles. We know the number of particles. It is 6.02 times 10 to the 23rd, which we know to be 1 mole. Okay. We already know the volume and temperature. I'm going to go ahead and highlight that for simplicity. The volume is the amount of space occupied period. Because there is so much space between the gas particles, the volume of a gas is considered to be the size of the container. We learned that at the beginning when we were learning the difference between a solid, liquid, and gas. Now the temperature, this is that Kelvin scale that I referred back to in the kinetic molecular theory. The temperature is a measure of motion, the measure of kinetic energy of the particles. More motion equals more temperature, or I'm sorry, not more temperature, I guess the word should be higher temperature, right? So more motion, higher temperature. The Kelvin temperature scale, so the Kelvin temperature scale is the only direct measure of motion. 0 Kelvin is called absolute zero, which means no motion. Therefore, there are no negative numbers in Kelvin. Okay, so when working with gas law problems, the temperature must be in Kelvin. We always must have it in Kelvin. So the temperature conversions are Kelvin equals 273 K So Kelvin equals degrees Celsius plus 273 K. Likewise, degrees Celsius equals Kelvin minus 273. Okay, so you do need to know these temperature conversions. All right, pressure. Gas pressure is created when the gas particles collide with the walls of the container. All right, the key word here is collisions. There's elastic collisions. The more collisions, the more pressure. What would cause an increase in pressure? I want you to think about that. What would cause an increase in these collisions? We could have an increase in temperature, right? Because the particles are moving faster, the more kinetic energy. We could add more particles, right? And then we could also decrease the volume. So if I have a balloon here, right? If I increase the temperature, maybe below it, if I have a hot plate full with gas, and it's increasing the temperature, it's going to have more pressure. If I walk out of HEB in the summertime, we've increased the temperature inside that balloon, and oftentimes the balloon will pop. We can add more particles to it. We can cut the balloon, and add same amount of particles, but a decreased volume that will also increase the pressure. Pressure can be measured in many units. Atmospheres, we're going to abbreviate that as ATMs. Atmosphere. Okay. Millimeters of mercury, kilopascals, and PSI, pounds per square inch. Now, so pressure conversions. 1 atmosphere equals 760 millimeters of mercury, which is equal to 101.3 kilopascals, which is equal to 14.7 psi. So let's do some converting. It's the same thing, underline the given. We start by writing the given, 125 kilopascals. The words on the top are the words on the bottom. So we look here, we see 101.3 kilopascals is equal to 760 millimeters of mercury. So let's see where we got those numbers from. So 760 millimeters of mercury is here. And 101.3 kilopascals is here. So that's where we got those numbers. Then, of course, we multiply across the top, divide by the bottom, and we get 937.81 millimeters of mercury. What I highly suggest that you do is you stop the video and you practice these on your own and then see how many you get right. And come back and check your work. Okay? So the next one is PSI. Start by writing the given, 22.5 PSI. The words on the top are the words on the bottom. So it's 14.7 PSI for every 101.3 kilopascals. So 14.7 PSI and 14.7 PSI. And then kilopascals I did in blue. Multiply across the top, divide by the bottom, and we have 155.05 kilopascals. Last but not least, 1.5 atmospheres. The words on the top are the words on the bottom. There's 1 atmosphere for every 760 millimeters of mercury.